Our next section, 6.5, is titled Applications of Common Logarithms. We want to be able to define, which we have done already in a previous section, the use of common logarithms, the functions, how to solve exponentials, logarithmic equations with them. So you can see some work, some equations in that, examples in that area. And then evaluate using the change of base formula, which some of you have been waiting for a while, not knowing what it is. All right, in 6.5, let's look at a little more with practical application. Sound intensity measured in decibels. It's also measured in watts per meters squared. When we talk about our scale, the decibel scale was created as a logarithmic scale, but you can hear sounds that measure from 10 to the second all the way up to 10 to the 12th. Very large interval, very large noise difference as well. So if we had the intensity of a certain dog's bark is about 600 times as loud as the threshold of hearing called I sub 0. Find the relative intensity R of this dog's bark in decibels. So we take that formula, decibels equals 10 times the log of the threshold of hearing is that I sub 0. And that's what that 10 to the negative 12th represents. So we are 600 times that for this dog. And so you can see right now that when you look at that, the I sub 0, that threshold of hearing, actually cancels out when you do the math. And all you have left is 10 times the log of 600, which, if you do that, because it is a base 10 common log number, you can use your calculator. Go ahead and calculate that, and we'll reveal the answer momentarily. So on your graphing calculator, you should be able to get a decimal approximation, do that multiplication, and when you finish, did you get approximately about 27.78-ish? That would be the relative intensity, okay, in decibels. So there's an example of using common logarithms in real life situations. Now, the problem has been we are solving equations in the form y equals b to the x. And when we solve those, we have a base that tends to be not a base 10 number, a power that's unknown, our variable, and that it equals some value. And that value usually is not a power of your base. So here is a way that you can use to solve any equation of that form, especially when we're not in base 10. But it says, step 1, take the logarithms of both sides, use the powering property of logs, and then solve b to the x equals a. Now, when we look at this, we should be able to talk about our base 10 and other bases. But let's take that equation, and according to these processes, take the logarithm of both sides. So if I have this equation, if I took the log of both sides, I would have log of the left side equals the log of the right side. Okay? And then it says, notice that we should be able to use the powering property of log. So that would mean that exponent of x comes down as a multiplier. So I now have x times the log of 3. And you'll notice now everything nicely is sitting on the same level. Then solve, which means get x by itself. We can divide both sides by that log of 3. And again, nicely on the left-hand side, we have some canceling that happens. And that'll leave x by itself. And now look, we have two numbers that did not start out in base 10. we have two numbers that represent base 10 situation, so you should be able to take the log of 57 and divide it by the log of 3, and that would be base 10. So go ahead and hit log of 57 on your calculator divided by the log of the log of 3. It's not base 3. They're both in base 10. And when you get that, you get a decimal value that is approximately 3.68-ish, we'll say, rounded to the nearest hundredth. And you can go back and say, well, wait a minute, how do I know I'm right? Well, before, remember, when we were doing this, we would say, well, 3 to the first, 3 to the second, let's go a little higher, 3 to the third. We'd be writing those powers of 3 because that's what this is about. And 3 to the third is 27. 3 to the fourth is basically 9 times 9, so 81. And you know that 57 falls somewhere in this range, which means it falls in between a power of 3 and a power of 4. So by trial and error, we can sort of see, yeah, this does work, but we'd rather have that more exact answer, which is what we got when we did our division. Now that is called the change of base formula. And I think you'll see it written over here. So the change of base logarithm says if you have a number in base B to that A that you're trying to solve for, you can take the log of that A value in base 10 divided by the log of that B value in base 10, and you will get that approximation that we needed. It is not a single keystroke, but it's better than nothing. So in this problem, we'd have to do the log of 100, which we have an idea what it is, but then the log of 4. Not a very nice number. So go ahead and do your division. Check it. I don't know what I'm rounding to. In this case, I went to the nearest thousandth. So log of 50 in base 2, again, you could do it in your head and approximate, say what whole numbers, but if we go ahead and do that division, we are doing the log of 50 divided by the log of 2, the change of base formula. Go ahead and do that division. So now you have a way to put non-base 10 logs into your calculator. All right, checking it. Whoops. You get a 5.644-ish. Again, hopefully got the idea. So the change of base logarithm. As long as it's not base 10, you're going straight to that division problem. The division problem should be the log of the number you're evaluating, so the log of 50. Again, not a nice number in base 10, divided by the log of 3. You never would want to divide those two numbers because these represent decimals. So it's really a decimal division that's going on with the help of your calculator. Try that one. 3.561-ish. Again, we're rounding to the nearest thousandth. There may be different directions on different problems. So you should be able to head to the next section, having a better understanding of how to do logs, maybe feeling a little confident because of this change of base rule that we now have.